All right, so hi everyone. Welcome to this second GECO webinar. I see that we are now almost 30 people attending. So this webinar is part of the Geothermal Emission Control Project dissemination activities. And after a first successful event with the Exergo Economics, Exergo Environmental analysis method, which the University of Florence presented, we are now basically going to talk about another aspect of the GECO project, which is the carbon storage in ultramafic rocks. So I will present a little bit the program first and share my screen now. So a small glance at the program of this webinar. It's basically organized in two sessions. The first session would be a general talk about the carbon storage in ultramafic rocks, and it will be presented by Chiara Boschi from CNR. And the second session would be talking a bit about the natural analogs of CO2 storage in ultramafic rocks and basically presenting the results of the GECO project. And these will be presented by Andrea Rielli and Eugenio Trumpi as well from CNR, the Italian National Science Research Center. So yeah, before we start basically with the sessions and welcoming our speakers, I will give a small introduction about the GECO project. So I will change the presentation and go to here, basically. All right, so a bit about GECO. So GECO is the Geothermal Emission Control Project, and it has basically the ambition to lower the emission of geothermal power production. What we are trying to do is utilizing here several geological settings and try to test the Carfix method in them. So basically the concept of carbonation and mineral storage in rocks in order to reduce geothermal emissions in different those different geological settings. With this, we want to try to basically increase the competitiveness of geothermal energy and create new opportunities in terms of business. So part of what we are trying to do is to turn the captured emissions into commercial products. Yeah, as I said before, basically making geothermal energy a much more viable, safe, and cost-effective energy source. The expected impact is also to generalize our outcomes, basically to yeah, to apply them in also other industries. So the GECO project has 18 partners. It's a very large consortium. It includes 4 industrial partners, 1 SME, and 13 research and development facilities. We have had initially 4 demonstration sites. So we had Hellisheiði and Nesjavellir high temperature site in Iceland, which is basically a basaltic reservoir. Then we had Castelnuovo high temperature site in Nasik reservoir type of location. Then we have Bochum, low temperature site. It's a sedimentary reservoir, and the Kizildere high temperature site in Turkey, which is a volcanic clastic reservoir. Then we added a new site, which is the Hveragerði high temperature site in Iceland, which would be the substitute for Castelnuovo, since we basically could not proceed with the demonstrations there. Yeah, so this is basically the general idea about GECO. I was going to show you a little bit where we're at in the project. So it's a 4-year project, which started with preparation and basic design and site characterization of the different locations chosen. Then in 2020 and early 2021, we were working on the design engineering of injection systems. And since the second part of last year and this year, we are starting the commissioning and the demonstrations of the different GECO solutions developed. So this is the general idea of GECO, and now I will welcome my guests today. CNR is one of the partners in GECO, and they have been managing one of the work packages that is related to this, the carbonation or like carbon storage in ultramafic rocks. So part of the project was to, or the main part of the project was to have in situ mineral carbonation, but what we are going to talk about today is the ex situ carbonation process, which the CNR team has been working on. So with no further ado, I will welcome Chiara, Eugenio, and Andrea. So if you guys could come in and turn on your cameras and microphones.
Good afternoon, everyone.
Hi, everyone. Hi. So I'll do like a small introduction of all of you. You can start, Chiara.
Yeah, introduction of myself. Okay. Good afternoon, everyone. I'm a senior researcher at IGG CNR, and I'm involved as work package leader of this task. So learning about CO2 storage in ultramafic rocks. And I'm working with Eugenio, Andrea, and other colleague of me on different aspects of the carbon storage in ultramafic rocks, especially in Tuscany. And of course, I will happy today to show some of our results.
Thank you, Chiara. So Andrea or Eugenio?
Hi, yeah. I'm a researcher as well at the National Research Council of Italy, and I've been involved since the beginning with the GECO project, and I'm a geochemist, and I've been involved especially in the field studies and in the all different aspects of national analog studies. So I'm going to present basically the results in the next part of the seminar, the second part of the seminar. And yeah, that's it pretty much.
Thank you, Andrea. Eugenio?
Hello, everyone. Eugenio Trumpi. I'm working for the National Research Council of Italy at the Institute of Geoscience and Earth Resources with Andrea and Chiara. I'm involved since the beginning in GECO Project. I worked mainly in the characterization of the Italian GECO site, and now here today I'm going to present to you the last part of this webinar related to a study we performed in the frame of GECO, aimed at the characterization of the potentiality of CCS in Tuscany.
Thank you very much, everyone. So I will give the floor now to Chiara to start with the general introduction on carbon storage in ultramafic rocks.
Okay, I share my screen. Please, Amel, let me know if the screen you see well, the screen.
Yes, it's
okay. I can go. Okay, good afternoon again to everyone. I'm Chiara Boschi from CNR, and today I will speak about a carbon storage in ultramafic rocks. So I want to give you a general introduction on this topic, and my colleague Andrea and Eugenio will tell you after me about results of GECO projects. If we want to make an introduction, of course, we have to start since the beginning of the reason of study this kind of technology. And we cannot avoid to plot this kind of graph. That is a graph that indicate you the increase of CO2 since decade. This increase stop, or we have a small decrease only linked to crisis. So economic or health crisis, as we have last year for COVID and pandemic situation. So each year, half of this emission are removed naturally from ocean and from the soil, but the rest of the emission, CO2 emission, contribute to global warming because it remains in the atmosphere. So the reason the Paris Agreement at the COP26 clearly state that we have to make our effort to try to limit the warming less than 1.5 degrees. And to limit this temperature increase, it's mean limiting CO2 emission. And for this reason, there are a number of institutions. The most famous, most important institution, IPCC, International Panel on Climate Change, they make a different scenario about how to decrease the CO2 emission and the fossil fuel use, increase the renewable energy, and so on. And all this scenario take into account also other variables like increased quality of life for poor people or the increase of population. Just to know, there is some estimation that from now to 100, we will be 10 billion of persons in the world. It means that the energy demand will increase. So this is the reason, because at the end, the IPCC state that also in the optimistic scenario, we need negative emission technology. So we need to remove carbon from the atmosphere or from point emission. And there are a number of options to do that. And the options are called in general carbon dioxide removal, include an increase of carbon storage in the soil, for example, or with the afforestation, or with the coastal blue carbon, that is a practice that increases the amount of carbon stored in living plant or sediment, or using biomass together with carbon capture and storage, or we can take directly the CO2 from the air. But of course, most of this technology includes geological CCS. I speak about geological CCS because it's the first technique that we start to study decades ago. And up to now, what we have that we store with CCS, geological CCS, only 206,000 million of CO2 cumulative. This is a cumulative amount. If we look at the scenario PCC, we need to store from now to 2100 from 348 to 1,218 gigaton of CO2 to keep the temperature below 1.5 degree. But this is not only with CCS. The scenario includes all the other technique and the efficiency of energy, renewable energy, everything, but still, in optimistic view, this is what we know what we need for CCS. It means that we need to store from 4 to 15 gigaton per year. To do that, we have to characterize, appraise, and develop thousands of individual storage sites. And to now, so the most famous CCS technique and is called long-term CO2 storage, or geological storage, has been developed decades ago, first of all with the enhanced oil recovery, or inject the CO2 in saline formation or in cold seam or in depleted oil and gas reservoir. But we want in GECO to be a step forward with respect to geological storage. We want to do mineralogical storage. Amel already introduced the fact that in GECO we study in situ mineral sequestration, ex situ mineral sequestration. One of the the mineral sequestration in general is a step forward to respect to geological sequestration, because after the injection in a reservoir, the CO2 is dissolved in the fluid, and after that, if we are in presence of suitable rocks, the new minerals are formed. And this kind of process has been studied since years in Carfix's project and now in GECO. And in Iceland, there are up to now, more than 12,000 tons of CO2 capture from the geothermal power plant and inject in the subsurface. And now in GECO, we want to, this is about 33% of the CO2 emitter in the geothermal plant in Iceland. And in GECO, we want to improve this kind of percentage to 90. And if globally, if carbon mineralization, this kind of rocks that in Carfix in Iceland are basalts, if we can do it because it's economically accessible, we can sequester a huge amount of CO2. We are, for example, here there is an estimation of 60 billion of gigaton of CO2. It's a normal potential that we can store. But what is mineral sequestration? It's a reaction. It's a reaction between basalts, for example, as in Iceland, or other rocks as peridotite, serpentinite, that are rich in mineral that are like olivine, that is the formula here, or serpentine, and in presence of CO2 this kind of mineral becoming stable, and they are transformed naturally in other kind of mineral. They are called carbonate, magnesite, or calcite, siderite, dolomite, depends on the cation that you have as feedstock, initial feedstock. And there are another things of this kind of reaction, that the reaction is exothermic, and you have energy as output. So this reaction occurs in nature, and this is the reason because we are studying the natural analog. So the type of reaction, this kind of process has been studied since several decades. But the reason, because we start to study for carbon capture, is because due to the warming and due to the global change. And in the in America, in USA, Lackner, Seyfried tried to hypothesize that these rocks can be optimum rocks to do this kind of methodology. And also because this represents the safe storage mechanism, because minimize the leakage that we can have in geological storage. Unfortunately, especially for serpentinite rocks, this approach is at lowest stage of technology readiness and is under continuing investigation and lab and study, as we want to present today. But what we know up to now, the degree to which the release cation for minerals depends on the elements, on the pH, on the temperature, on the geological setting. For example, what we know that calcium readily reacts with CO2 in aqueous solution at temperature below 300 degrees, forming calcite or aragonite. Magnesium, if you have a magnesium-rich silicate or oxide, precipitate as magnesite, as we already saw in the previous slide, and dolomite at temperature above 65 degrees. A lower temperature, we have another range of mineral, another type of mineral that are called hydrous carbonate, that are in the family of hydromagnesite, dipingite, or nesconite can form. So we need acidic CO2-rich water, then react with our rocks that can be mafic or ultramafic, and we need a dissolution, partial or total, congruent or incongruent dissolution of silica mineral that liberate calcium, magnesium, iron, and in presence of CO2 form carbonate. Another reason, because this technique is very fascinating and also with high potential, that we have a number of basalts and serpentinite peridotite in all over the world. This is a map they take from a review of Kieleman of 2019 that show the sequestration facility, the project, but also the opportunity. And the opportunity are split in sedimentary reservoir, where we can do only geological sequestration, and basaltic formation and ultramafic formation. So we can see we have a large number of outcrop and not outcrop, but in deep formation that we can use for CO2 in situ, CO2 mineral sequestration. But we have other options. The other option are called ex situ mineral sequestration. Here again, we have the similar sketch that we used at the beginning, and on the right there is one of the type of 100 type of scheme that summarize the type of the plant that we have to build up for ex situ. In what consists? We need some outcrop or mine waste or rocks, ultramafic rocks, for example, that we can use. We can crash, mechanically crash to react. We can use a feedstock to react with CO2. The way to do that, it's very changing from time to time. Someone decide to enhance this kind of reaction by crashing the rocks. Crashing the rocks, it means that you can have more surface of activation, because the rocks are powder, and the powder can easily more react, and you can speed up the rate of reaction. Otherwise, there is other method. For example, with chemical treatment, with acid, not only CO2, so not only HCO3 minus, but also other acids can try to dissolve faster our silicate. Or again, we can also have a temperature increase that can help, or pH switch. For example, another type of method incorporate the fact that at the beginning of the dissolution, the pH has to be acidic pH, so low pH, and after you switch in high pH for the precipitation of magnesite. So in situ, ex situ, and we have another option, superficial. This is something that born in Canada, but also we have the same example in Tuscany. There are some conditions, especially for mine tailing, where CO2 can be sequestered naturally from CO2 from the atmosphere, because there are conditions where the rocks are already powder, because they are a waste of mine operation, and easily can react with the CO2 of the atmosphere. It's very difficult to make an evaluation, for example, especially for the ex situ condition, of which method is the best, because the conditions are changing from one scheme to the other scheme. The only things that we can say, for example, is to see the kinetic of the reaction. And the kinetic reaction change from mineral to the other mineral. And for example, this is another scheme that can plot the dissolution rate. And we see that one of the most suitable minerals we use for ex situ, but also in situ mineral sequestration is wollastonite. But wollastonite is not so common in nature. So we have not the amount of wollastonite that can be exploited for our purpose. Otherwise, we have olivine. And olivine is the mineral that react, for example, on the plant in Iceland, because olivine is rich also in basalts, not only in peridotite and serpentinite. And olivine is very good feedstock for our purpose. Otherwise, we have serpentine. Serpentine is the main mineral in serpentinite, in the ultramafic rocks. Serpentinite are hydrate peridotite, and serpentine is about 90% of a typical serpentinite that we found in the oceanic floor or in our ophiolite. But serpentine, has a very different behavior, because it's not really easy to dissolve. But together with serpentine, we have also brucite. Brucite is another mineral, accessory mineral formed during serpentinization. It's an oxide of magnesium. This is a very, very nice mineral for us because brucite is weak mineral and it very fast can dissolve in the water. And we will see in our study how brucite is important and how is the behavior of serpentine. But so to enhance our carbon sequestration, but also to enlarge the potentiality of sequester CO2 in rocks, as in situ, not only in basalt, but serpentine, we have to solve a number of problems. Because in ultramafic rocks, we have the positive side that this, okay, the reaction is isothermic, and CO2 is incorporated over geological time into stable magnesite, and we have large serpentine body worldwide. But at the same time, the carbonation process do not go to completion. And this is something that we found in the lab. And we observe also a decrease of porosity during reaction, and as we see before, a slow rate of serpentine dissolution. This is our starting point of the project. This is our starting point since several years because we have a difference between the lab experiment and what we see in the nature. So the lab experiment say us that it's very difficult to make carbon capture and storage in ultramafic rocks. Also because another thing that I forgot to say, that serpentinite has no permeability, no porosity, but the only porosity that we found serpentinite are secondary porosity. It's something that happened due to the reaction, but is not for natural porosity that we found in basalt, for example. And the fact that during the lab experiment, the porosity start to decrease, it's because you form magnesite, and this magnesite close the secondary porosity of the rocks. So the starting point was this one, and this is the reason because we found a very interesting topic to learn from nature. This reaction happens naturally, as is one of the main weathering or hydrothermal reaction that captures CO2 and in our surface, but also below the surface. This is enter in the global carbon cycle. So the weathering of the serpentine rocks and ultramafic rocks are one of the main component of the carbon cycle. So what we want to do, what we did, is go to the field and see what happened in nature. Here, I just want to show that this kind of process has been studied not for CCS, but for other reasons since many times. And we found that with the same process happen a different condition, PT condition. We start very high pressure, high temperature, and we found liswanite. Otherwise, if we increase shallow alteration, we decrease pressure, decrease temperature, we found ultramafic rock-hosted vein and partially carbonate matrix. Or a very superficial, we found ultramafic rock-hosted vein. In general, for example, the first example is the liswanite. Liswanite is formed by alteration of serpentinite, high temperature and high pressure, through a complete dissolution and precipitation. Liswanite has not been studied for CCS, but because in liswanite, especially in Russia, for example, but also in the Urals, but also in California, in Oman, but especially in Russia, was studied because it contained gold and was tried to find a way to explore the gold resource in these rocks. But this comes from a completely alteration, massive carbonation, and the assemblage is completely different from the protolite. We have magnesite, quartz, talc, chromium muscovite, chlorite. We can have different kind of mineral assemblage, but this is the fundamental that we have in all the currents of liswanite worldwide. So as you see, the pressure is very high. It's up to 1.4 gigapascal, and the temperature can go up to 400 degrees. Normally, we assume the listenai are forming subduction setting, geological setting, where, or another type of formation is abduction process. So a process that imply the fact that the pressure is very high, the temperature is very high. The CO2 and H2O come from a deep source. If we go more superficial, we have a different kind of situation. So in this case, the rocks are not completely massively altered, but the deposit of magnesite that usually come with opal CT and clay mineral are restricted to vein. So we have a fracture system, and along the fracture system, magnesite stores CO2 and form and deposits along very long vein that can be long several kilometers and 100-meter wide. And this kind of process has to be assumed to happen at temperature less than 200 degrees and a kilometer and 1 kilometer depth, less than 1 kilometer depth. As you see that the structure, we can have a very intrusive structure of veins. So the vein intrude and form this kind of structure, and most of the time is isotropic, or sometimes it's tectonical driven. This is a sketch from Paul. You see, it's Paul. This is a very famous past paper in the 90s. So this kind of process has been studied not for CCS again, but now we can turn this study for enhance our process for industrial use. And we go more superficial again, and we found a nodular vein magnesite in weathering profile. Here there is a soil, a weather serpentinite, and below serpentine plus magnesite. In this case, magnesite come with opal, but this is opal A, that this is typical of more superficial condition. This is generally a condition very oxidative, and the magnesite that form this kind of magnesite nodular like this, it's formed with very poor. It's almost an end member of magnesite, no iron on it. This kind of precipitation can be or post-tectonic, so tectonic doesn't affect in any way the type of precipitation, or can be tectonical driven, but only just to have a number of veins that are oriented in the same stress field of the area. In this case, the CO2 is debating because or can be atmospheric or organic, because CO2 can take from the soil, and rainwater take this CO2, organic CO2, and bring this CO2 in the weather serpentinite, partially dissolve serpentine, and form magnesite. And of course, H2O is meteoric. And finally, the last, very superficial, again, that it's what we say superficial CCS. We have a natural analog also for these, that what we found in Canada, in mine tailing of Canada, with form not magnesite at the moment, but hydrocarbonate. This kind of precipitation is daily precipitation, very, very fast. But the minerals that are formed not well stable. Some are very metastable, but it's hydromagnesite, nesconite, dippingite. And the same type of occurrence is found also in Tuscany. And the next talk we will speak about that. And we found in outcrop, where we have some not very massive rocks, and they are completely transformed, not completely, so sorry, coated with this whitish mineral. They are hydrous carbonate. Otherwise, we found a similar occurrence also in the copper mine, serpentinite hosted copper mine, that you find the wall completely whitish, and where we have a thin coating of hydrous mineral. This kind of carbonation is used also for a number of remediation. For example, we try to figure out how we can solve the problem of asbestos, because sometimes, especially also in Canada, but also in Italy, asbestos is forbidden, but we can use this kind of process for asbestos mine tailing, as in Canada, for example, they are already doing that. So in general, we have a number of processes that form completely and go to completion with carbonation rocks, from massive to vein to superficial occurrence. This is mean that we can try to figure out how they work, and we can try to reproduce this kind of natural occurrence for our industrial use, and also enhancing the reaction in case we don't want to go to such deep pressure as the case of listronite. Listronite, of course, is the best option, but of course it's too expensive because we need to have a very high pressure and high temperature. The other occurrence can be more reproducible, and especially for in situ or ex situ situations. So yes, we can do CCS, mineral CCS in ultramafic rocks. We have to learn how to do it. And this is the reason because we try to do it to solve in the GECO project. Thank you very much.
Thank you very much, Chiara, for the very insightful, very informative talk. I think, yeah, we have a lot of ways to do mineral carbonation in the ultramafic rocks, and it's quite fascinating because this is opening new opportunities basically for carbon sequestration in other contexts than basaltic rocks as it was done until now.
Yeah. So I forgot one option. Sorry, I was that the same type of process. Can we try to apply also for waste material? This is another slag, fly ash, and so on. The important things are we need magnesium or calcium, or some that can react with CO2. So this is enlarge again the potentiality of CCS and mineral CCS.
Definitely, it's a field that is now quite flourishing, and I think it's time to push that boundary forward and explore new ways and new applications for it. So yeah, so it's time for the Q&A session for the first session. So if our audience has any questions for Chiara, please drop them in the chat, and she'll try to answer them.
Or we can do all together the question all together after the result, as you want.
We could do that too. Like, have a quick question for you. I mean, you were talking about several ways to do the mineral carbonation ultramafic rocks, but what, in like a nutshell, what would be the most ideal way to sequestrate carbon in an ultramafic body in terms of hydrology or depth or yeah.
Depends on what you want.
Yeah.
What do you have? Of course, if you have a layer of serpentine very well defined, confined in impermeable rock and cap rock, of course, it would be nice to have in situ sequestration in serpentinite, as we are doing in Iceland. But for example, if you have main waste, we have in Tuscany, also in Canada or in other places. It would be nice also to use as feedstock and grinding the rocks and use for carbon sequestration ex situ. So we have a range, an umbrella, a portfolio of options, and depends on what you want and where you are. Because one of the things that you have to think about also to be very close to the point source of CO2. Because of course, if you have to make a pipeline of CO2 of 100 or 1,000 kilometers, this doesn't make any sense to do it.
Oh.
So it's geological dependent, the choice that you have to do.
Definitely, and this is what we're facing now in the GECO project. We have different geologies, and it's quite interesting to explore that. So we have a question that is coming up from Ferretti Eugenio. So yeah, thank you. So Eugenio says, has it been considered in this direction, hornblende rocks, and in case, what are the pros and cons?
So hornblende rock we didn't use yet, but it's true, there is magnesium. Of course, we have to see, and also magnesium rich amphibole, and this is good, but we have to see the kinetic of the mineral. First of all, the most lab experiment has been made with olivine, serpentine, brucite, the plot that I showed you before. But of course, all the minerals that contain magnesium can be feedstock, but depends of the kinetic of the mineral.
Yeah. One more question regarding the context. So do you think it is possible as well, because we have ultramafic rocks that are of oceanic origin, but you have also the continental ultramafic rocks type. What's your take about the mineral storage in the continental?
Oh, you mean if I like more continental sequestration in situ, or?
Yeah, what do you think about the feasibility of it in
Okay, I think at the beginning, especially when we start to speak about mineral CCS in peridotite and in basalt, we think about oceanic sequestration. But of course, it's more feasible in continental way, because we are more close to point emission source, for example. And most of the time, the depth where we have oceanic floor, so oceanic lithosphere is more than 1,000 meters. So this will make a big question and big cost.
Yeah, definitely in the localities, it's quite limited. I mean, we have analogs for ophiolites. You have the Oman ophiolites, you have the in Tuscany and other places, but the continental mantle is not showing or outcropping in many places. You have the Ronda peridotite in southern Spain and Beni-Busra in northern Morocco, and it's quite rare to find that, but
I'm not completely agree, because from the calculation we did, and Eugenio will show you. Also, if you have a very some occurrence, not small but some, the potentiality of these occurrences are huge compared what we need. So and this is the time that we need all. And all this outcrop can be used, especially if are well confined and the CCS is safe and we are out of any dangerous or tectonic active situation. This can be done.
Yeah, I was talking like more about the geographical distribution. We have only like a few, but definitely, I mean, there are serpentinite rich zones in there. Another question from Atena Rosa. So referring to in situ reactions, I expect that geomechanical behavior would change. Should we then consider also the possibility of decrease in site stability?
Because you jumped one question. Was a question before?
Was there another question? Yes, I'm sorry, from Alicia Lachenka. So let's answer.
First, I will answer the second one, and after. So I expect the chemical behavior will change. Yeah, of course. This is something that we have to do it. First of all, we have to try a pilot plant. I cannot say in advance what happened. Of course, one of the project, for example, was in Oman, and now not anymore, because we are far away from every city, every town. And the stability can change, but I'm not sure that we can have a very dramatic change, because some of the major problem is the porosity. And the porosity can try, if the porosity will tend to zero, now you have an overpressure. But this is something that happened also in all the geothermal field, and you just pump water to reproduce another new fracturation. So this is is something that we have to take into account. But first of all, we need to try in safe place and to monitor what happened to the porosity. That is the big question, is porosity in serpentinite.
Yeah. Thank you, Chiara. So Alicia's question is, in my opinion, the waste materials, magnesium, calcium-rich tailings, present a real opportunity, reducing waste hazard, maximizing metal outputs, less energy needed for physical pretreatment, and we need international collaboration to progress with mineral carbonation beyond the relatively low TRL level. That's totally agreed.
Yeah, I'm totally agree with Alicia. We are trying to write down proposal because this is a W good effect. Because in one place you sequester CO2, in other ways you produce an end of waste. So you produce a new material that you can use for other purpose, for road, for building house. So for example, the fly ash, now it's more and more common that they ask us to try to make carbonation of fly ash. At the moment, fly ash are waste material and also dangerous waste material. And now they have to put in a special place because we cannot use. With carbonation of fly ash, we produce end of waste, and we can use again the fly ash for other use. The only problem that we have in this waste material and the presence of metal. So if we have any dangerous metal, we have to find a way to separate or to I don't know, to try to keep this metal before the carbonation or in a different way, because otherwise you have a problem that, okay, you carbonate this material, but you cannot consider this material end of waste. And this is the important results from waste to end of waste. And this is what we can do.
Yeah, and that's definitely maybe relevant to circular economy concept where we need to think about the whole process and not just
exactly.
And so, yeah, thank you. I do not see any other question. It's 10 minutes to 2 Reykjavik time and to 3 Central European time. So maybe it's time for a break before we move forward to the session number 2 with the natural analogs and the case study of the Tuscan ophiolites. So see you at 2 o'clock Reykjavik time.
3 o'clock in Italy time. Okay. See you later.
Yes, see you. So welcome back, everyone. It is time to dive into the session number 2. So the session number 2 will be about the natural analogs of CO2 storage in ultramafic rocks. And Eugenio and Andrea will be presenting results from the GECO project. So Eugenio, no, Andrea, the floor is yours to take. You are muted.
Okay, yeah.
Okay, now, yeah.
So I think I will share my screen. Just a second. There we go. I think you can see my screen now.
Not yet. You
Not
probably
yet.
shared a different screen.
Okay, sorry.
No worries.
Try again. So, or this one now it's working better, I think.
Not yet. Okay,
Yeah.
no.
There we go.
Perfect.
Okay, so thank you everyone for being here. And my name is Andrea Rielli. I'm from the Italian Research Council. And in this part of the webinar, I will build on what Chiara just said in the first part. And I will give you an overview of the results we have got from the study of natural analog during the GECO project. So first of all, I wanted to give you an introduction to let you understand how the motivation for this study and why we use the natural analogs. So This study fits in the GECO project, specifically in VP3. We were leader of task 3.2, and our aim was mainly to understand a way to sequester CO2 with interaction with ultramafic rocks and produce carbonate mineral that then can we use as construction material, basically. And we started our work with a simple thought in mind, basically considering that the current limitation to this technology are the slow reaction rate and the low efficiency of the reaction. From the other side, we also knew that there are experiments, and we have the technology to make this reaction quite fast and efficient, but it comes with a strong increase in the cost of the storage of CO2. So somehow this is limiting the application of this technology because it becomes economically unappealing. So we try to see this problem from a different perspective, and in particular, we ask ourselves whether we could find natural systems that have overcome this kind of limitation in a different way. So for this reason, we looked to natural analogs, and we were quite fortunate to have here in southern Tuscany several examples of spontaneous carbonation. So basically, we are here in northern central Italy, and in particular, we centered our study here around the Castelnuovo demo site. As you can see, there are lots of green patches on this map, and they are all ultramafic rocks belonging basically to the Ligurian ophiolites. Ligurian ophiolites, which are the remnants of an ancient ocean and also lithospheric mantle associated, which has been overthrusted to the continental plate of the Adria margin during the Apennine orogenesis. Then after the emplacement, basically on the Apennine chain during the extensional phase, this ophiolite has been dismembered and eroded to the surface. That basically leave us with this kind of geological setting you can see on the right side of the screen. And as you can see, there are also lots of dots, yellow and blue. And these are all analogs that we have found and characterized and studied for this project. So going back to our first question was that could we found analogs that have overcome this limitation? Actually, we found something that have overcome this limitation spontaneously during the natural process. And we selected two members. So the first one, we decided to study the first one because we see that it's quite fast considering geological time and also the very low temperature at which it takes place, because we see that the spontaneous covering of ultramafic outcrops by a series of hydromagnesite and different hydrous carbonates. So we studied this spontaneous carbonation at low temperature to see how it could happen so fast. And the second member, instead, we wanted to solve the problem of low efficiency of the reaction and understand how nature could be efficient in the formation of magnesite deposits. And these are the vein type deposits that Chiara showed before in the first part of the seminar. Here we can say that the carbonation reached a really high efficiency because we see that almost the serpentinites are completely reacted with the fluid. So almost 90% of the initial rock is converted into magnesite. So in this presentation, basically, I'm gonna give you an overview of these two members and show you how we work with them and how we could answer these two questions from a natural analog perspective. So starting from the first one, which is located right here, right north of the Castelnuovo demo site. And we choose the Monte Castelli ophiolite complex because it offers, as you can see, a very nice exposure of a cross-section of a lithospheric mantle, thanks to this fluvial erosion, which basically cut north-south this ultramafic massif. So here, how we approach the study of this and the member was basically from a multidisciplinary perspective, starting from the field geological mapping, which was basically aimed to see where the natural and spontaneous carbonation took place in this environment, and also to check whether, to check if you want the natural alteration of a great variety of ultramafic rocks, because we found, thanks to the amazing exposure we have there, almost a composition, a variability of composition in the ultramafic rock, which encompass all the classification of the ultramafic system. And what we saw was that only a specific type of ultramafic rock, which is called dunite, which is basically a very olivine-rich peridotite, reacts very quickly with CO2 at low temperature. And we could see that when working in the field, we crossed an outcrop that was freshly exposed by fluvial erosion and landslides, like as you can see in this picture here. So what we realized was that when we have the association of Habsburgite, for example, and dunite, only the dunite becomes covered by this white patina. And again, so this process we also found that was not very restricted to small outcrops, but could also cover entire outcrop like the one you see in the left side picture. So this is a person phosphor scale. You can see that this is a quite large outcrop, completely converted into hydromagnesite. On the right side, instead, you can see how this process is pervasive, it's very strong, and completely cover every inch of exposed rock to the surface. So you get a complete cover by hydrocarbonates of any outcrop of dunite. How this process proceeds macroscopically, basically starts from the discontinuities in the rocks. In this case, we have dunites with these large magnetite veins. They are discontinuities where water can infiltrate, and as it emerges to the surface, it precipitates this assemblage of hydromagnesite and layered double hydroxide, LDH, which are basically a continuum between pyrrhorite and chollingite. And the end results of this alteration is the complete obliteration, as you can see in the right picture here, of the outcrop. So in this study, we perform petrological and geochemical investigation to understand why only dunite was so fast in sequestering CO2 at low temperature. And what we found was that dunite produced differently than Habsburgite, a mineral, specific mineral during serpentinization, which is called brucite. Brucite, as already Chiara told you in the first part of the webinar, is a very reactive mineral at low temperature, is a magnesium hydroxide, and it basically dissolves order of magnitude faster and easier than serpentine. And so this could allow the dissolution of brucite when meteoric water infiltrate the rock at low temperature, liberate magnesium, that then, in presence of CO2, will form hydromagnesite or LDH. So we found here a first-order lithological control on the speed of carbonation, just because dunite can produce this kind of specific type of mineral. Instead, Habsburgite, it doesn't produce during serpentinization brucite, and that's the reason why it doesn't form any carbonate at low temperature in the field. Then we found also a second-order mineralogical control, in this case on the efficiency of carbonation, because what we saw was that the mineralogy of brucite induced different type of carbonate assemblages. More specifically, when we found iron-rich brucite, when interacting with CO2, this assemblage produced a carbonate assemblage dominated by LDH with hydromagnesite. Whereas if we had iron-poor brucite in the first place, during interaction with CO2, we ended up with hydromagnesite. And as you can see, hydromagnesite contain almost an order of magnitude more carbon than LDH. So these mineralogical difference have a really high impact on the efficiency of carbonation. So two kind of control due to the mineralogy of the rock and the lithology. So going back to the first question, we could find that natural system overcame the slow reaction rate typical of spontaneous carbonation by targeting a specific type of ultramafic rock, which is dunite. Now, moving on to the second analog, here I'm gonna talk about the results we have got from the study of the Castiglioncello magnesite deposit, which is located here in the Livorno Mountains, a few kilometers north compared to the previous site. Here, as you already can see on the right picture, the carbon mineralization took place in a completely different way. So here, basically, this is a person for scale again, and we have a very large vein of magnesite, plus or minus dolomite and opal CT, that are hosted in a structurally controlled system in ultramafic rocks that have been altered at hydrothermal condition. So these basically are epithermal systems that have sequestered CO2 and formed this kind of rock. And what we did here was to use the same approach to the study of the natural analog we did before. So starting from a geological field map to build cross-section, and then moving on to petrology, isotope geochemistry. And also we did some more advanced analysis like CT scan and micro CT scan in collaboration with Utrecht University. And also we did some synchrotron XANES and elemental mapping to understand the distribution of elements and their speciation during alteration. And this work was also done in collaboration with the Australian Synchrotron and Monash University. With all this study, we had some very interesting results, and here I'm going to be focused on showing you basically the reason why this system was so efficient. So really simply because what we saw in the field was completely different from what we tried to replicate in laboratory experiment, because as you may know, in experimental carbonation, we try to dissolve the feedstock, the silicate mineral like serpentine, to extract magnesium. Instead, nature did something completely different and did not dissolve, of course, serpentine, but it transformed it into something else, basically an assemblage of clay minerals, as you can see in this central picture here. So there are some really good advantages in this method of extracting basically magnesium from the feedstock, because we have a really high efficiency release of magnesium. Almost all the magnesium is released by this conversion, but at the same time is coupled with the sequestration, with the consumption of CO2, SiO2, so silica. And this means that we overcome a really high, really important problem that we also have when we dissolve serpentine in experiments, the release of silica. Because we know that silica, when it's released during the dissolution of serpentine or other silicates, during carbonation experiments tend to form a passivating layer that inhibits the reaction. Basically, it shields a new mineral to get in contact with CO2-rich fluid, and so the reaction basically stops. So we see that in this case, the national analog tell us something completely new, that is basically to extract the feedstock, the magnesium or any cation from the feedstock material. It here was extracted to alteration and not to dissolution. So this is another information, and this is just the last slide to conclude, where I wanted to show you that how basically our workflow for this task, and how the study of natural analog fits into a methodological approach, where basically we start to look at what has been done by nature in the field, and then that of course can give us answers and inspiration for new experimental approaches. But then we need to still test them in the field, in the experimental, with an experimental approach, and that's what we did. And then we moved on to reaction path modeling to basically optimize the reaction. And with this slide, I thank you for your attention, and I conclude. Thank you.
Thank you very much, Andrea. I give the floor now to Eugenio, who will talk about the future and potential of the CO2 storage in the ultramafic rocks in Tuscany. Eugenio, you can go ahead.
Yes, let me
Eugenia, you're muted. Somehow you're still muted, but I can see your screen and the presentation.
Yeah, sorry, I didn't find the button because it was hidden by the stripe on the screen.
No worries.
Okay, I share again the presentation. Hopefully,
It's okay.
Yeah, in a shared mode.
Yeah.
Okay, let me start the presentation. Okay, I'm going to talk to you about the potentiality of CO2 storage sequestration in ultramafic rock in Tuscany, and I would like to mention at the beginning that in this exercise we performed in GECO Project, we worked at a very small scale. I mean that we worked at the Tuscany scale. So it means that probably the result we had should be improved and enhanced in each specific favorable areas. In the presentation, I'm going to show you even the methodology we used to obtain this this potentiality, and the most important thing is to highlight and to find the best parameters or factor that influence a location to be a potential site for carbon sequestration. Later, I will show you the dataset we used and, of course, the results. Thanks to the presentation we had before, I don't want to go into much detail explaining the reaction we are talking about. What we need to know for our exercise is that one of the parameters we are looking for is the existence of the ultramafic rocks. I mean, in the underground or cropping out. We are lucky because in Tuscany there are a lot of outcrop of serpentinites or ophiolite rocks, and we are even lucky because in the southern Tuscany, and there is an anomalous geothermal gradient. You can see here just a very rough estimation of potential we have here in Tuscany, but as you can see later, we refine a little bit more that those numbers. So going into much detail into the methodology, first of all, we have to say that we work in a GIS environment, geographical information systems, where we are able to combine different kind of information in the form of maps. Different information have to be firstly converted in maps, and then thanks to GIS operation is it possible to obtain favorable maps for different kind of phenomena. And in our case, of course, our topic was to found the most suitable areas for ex situ and in situ carbon sequestration. Yeah, this is simply the workflow. First of all, of course, we collected the data and we stored them in a geodatabase. Then we produced the thematic map that afterward have been combined to create the final suitable maps. this way of working is based on the concept of the it is based on the knowledge on a knowledge approach. So the team who worked on that activities on those activities helped with the experience to combine the layers in the best way. Here just a rough introduction on what were the used GIS operation, because the layers we had in the beginning have been geoprocessed. This is the right term to obtain different stage of computation. Those operations were the buffer, which is a sort of the GIS creates an area around a certain point. We use the dissolve to merge to unify the boundaries based on a common attribute values. We use the difference. You can have here in this slide some example of what the operation does, and the union. As said before, we focused on what were the most favorable parameters and unfavorable parameters for both the cases. We started by analyzing a surface geological map. We obtained it from the Tuscan region in their geological map repository, and then we used a large database we have here at CNR related to the information in the underground, because that database that I have a slide later on, but this is a database where deep boreholes are stored in, and many information from boreholes have been collected during the time. Then still in this database, and thanks to the National Geothermal Inventory dated late 80s, we had the map of temperature at a certain depth. We got even information related to hypocenters, so earthquakes, from the INGV EasyDay database. We had and we collected even information from again from Tuscan region related to the protected natural areas and landscape, and then we collected even the natural CO2 degassing point in Tuscany, and even from the HARPAT agency. We have a data set related to the CO2 degassing from industry. As mentioned before, we have at CNR a large database which has a very long story, because the information were collected since the 1988, and during the time, and thanks to different projects, mainly geothermal project, this database has been implemented and improved. Information, as said, related to the deep borehole are stored in together with the information on thermal manifestation. Moreover, some geothermal map are even collected and stored in. Yes, this is the first layer we used for our exercise. You can see here a geological map, and in green, in light green and dark green, you can see the the rocks related to ophiolites or ultramafic rocks. GIS operation in this case was digitization of the as areas of the area of the area where those lithologies are cropping out. In this image, you can see in black the ophiolites outcrops in Tuscany, and in red are the location of the boreholes where we collected information of ultramafic rocks. We use union and dissolve GIS operation to create this thematic layer, which is one of those we will use for the final suitability map. Regarding the ophiolites, which are exposed and cropping out in Tuscany, the area was about 339 kilometers square, and we registered variable thickness of these outcrops, ultramafic outcrops, ranging from 10 to 600 meters. Regarding the borehole, instead, we assuming that only the 20% of the thickness, because here we create a sort of model, a volume in the underground, starting from an average thickness of this ultramafic rock recovered into the different boreholes. The average thickness was 155 meters. Again, from geological surface map, we obtained even the by using, of course, GIS operation of union and dissolve, a layer in yellow, you can see here in the image, representing the neogene deposits in Tuscany. This layer is important mainly for the in situ sequestration, because we need the cap rock. The cap rock is a crucial point, because otherwise, if we inject CO2 in the underground, it is easy that in some way CO2 can rise again to the surface. In this case, the average thickness of this sedimentary cover was around 160 meters. Then, as said, we worked on a temperature map at 500 meters. This is the representation of the temperature at that depth. And you can see the two red areas related to the known geothermal system here in Tuscany, Larderello, Travalle, and in the southern part, Montamiata. And we use, again, GIS operation to firstly georeference the original raster map, and then we digitize it. To obtain the thematic layer related to the temperature, we classified the different areas in 4 classes. From the lowest favorable areas to the highest favorable areas. Then I'm going to show you here some unfavorable parameters or factor. Here you have in green a vector map obtained again from the Tuscan region related to the important community sites or zone of special protection or landscape bound. So all these three layers have been dissolved and unified together to get one layer, one unfavorable layer. Again, we worked even in the dataset coming from INGV. This is in the image you can see that we classify the different events by the magnitude and the depth of the hypocenter. As you can see, most of the events occur in the Apennine, and 65% of this occurrence have the hypocenter located between 3 and 9 kilometers in depth, and the magnitude average was around 1.5. And this is considered again as an unfavorable thematic layer. Here, coming from the GOGAS project and its database, we collected this information. This is the natural emission of CO2. You can see the different color of the bullet. The different color is related to the flow from the ground of this CO2 coming from the underground. The violet point are those locations where we do not have we did not have the measurement. So here we have the elaboration of the ex situ favorable areas for CCS. Rounded in red, you can see the two largest areas, which are related to the Riparbella and Santa Luce quarries. And for the identification of this area, we combine the outcrop of ophiolytes and we remove from those areas the areas related to the environmental restriction. It was a different GIS operation, actually. Here are some numbers. The CO2 mineral sequestration is up 86 kilometer cubed, considering an average thickness of 0.3 kilometers. This is equivalent to 232 gigatons of ophiolytes that could theoretically be mined, and 110 gigatons of CO2 could be potentially stored. Regarding the in situ favorable map, as you can see here on the left side, are listed the two favorable parameters we considered. So I mean the buried ophiolytes and of course the safe cap rock and the high temperature, which facilitate the reaction mentioned in the previous presentation of the webinar. As unfavorable parameters and thematic layer, again, the earthquake, the existence of earthquake, the CO2 natural emission points, and the landscape bounds. To obtain this map, we proceed in different steps. First of all, we combine the favorable parameters, and then we use the unfavorable parameters to obtain the final map. The boreholes where we had the Ultramafic rock have been processed in GIS to obtain to pass from a point which is related to the borehole to a possible area, and we create a buffer of 1 kilometer around each point, and we merged all this area. Then we score, as I mentioned before, the temperature map, and we combine the borehole buffer and temperature map. From this result, we remove firstly the environmental constraint, then a buffer areas related to the of 500 meters of CO2 natural point emissions. And then we remove even a buffer of 1 kilometer for each earthquakes location with the magnitude higher than 3. The final map, of course, is very simple. Only a few areas have been retrieved. The most favorable are the large area you can see in the center of the map, which include Pomarance, Montecervo, Lustignano, Monterotondo, Marittimo villages. There is an area in the north of Chiusdino. The area is known even with Travale, while the less favorable areas are Rocca Tederighi or the area very close to the Pieve Santo Stefano well. Here you can see here some results. If we consider 150 meters as a thickness for the ophiolites, you can compute a value of 26.4 kilometer cube of exploitable volume, which is equivalent to 71.4 gigatons of ophiolites. Well, actually, I made a mistake because, well, the sequestration of CO2 is up to 26.4, and which is equivalent of a volume of 71.4 gigatons of ophiolites. Sorry. Yeah, this is the last part of the exercise. This is something that was mentioned even before by Amel and Chiara in the discussion, because we were talking, if you remember, about the possibility to use these potential areas. So here you can have the emissions, the area where in Tuscany we have the highest emission from industry. You can see, of course, the Valdarno areas, surely, but even Piombino and other spots. And we combine this map with for example, for the ex-situ areas, you can see, well, actually it is a little bit small, but I circled in red the two most important areas, and I put even some arrows to describe the distances that are evident from industrial centers to these areas, to this favorable area. And I reported here on the right side the kilometers, so you can see that the distance are very small. It means that actually these areas can be used. As the same, I did the same exercise for the in situ areas, and you can see on the right side the kilometers computed in a GIS. This is actually the last slide. What I would like to leave and to remark is that as you saw in this presentation, we performed a study at small scale, at the Toscan scale. So if I remember, there was a question on geomechanics implication in sequestration and so on. I would say that this is the first step of the study. What we need now is to focus on the favorable areas we have already found, and then we can pass to simulation and modeling that thoroughly can provide results. And that's all from my side. Thank you. If you have any question, don't hesitate.
Thank you very much, Eugenio, for this very insightful presentation as well. And I will ask Andrea and Chiara to come forward for the closing words and perhaps any questions from the audience on the second session or on the thematic as a whole. So please feel free to drop your questions in the chat. And yeah, our speakers will answer them. So really like insightful results from this the study in the Tuscany ophiolites. I think it's opening definitely new doors for new applications of CO2 storage. A question would be like, how do you see this evolving? If there is a feasibility for it to happen, then how do you see it evolving in terms of applications, like whether attracting the construction material industry, or in terms of the environmental aspect? How would it look like? How would the dynamics look like? Eugenio showed a lot of information regarding the distance between the industrial zones, whether it's ex situ or in situ. We definitely know that the fractures can be a plus, but also a minus in terms of earthquakes or an alternative for porosity in these rocks. So how do you see this materializing in the future?
Do you want to answer me or?
Any of you, but you can start, Eugene, if you want.
Well, yeah, this was the first attempt we performed recently. What can I say is that, for instance, that we consider those parameters, but I would say that those are not the only parameters we can use. For surely, it is a matter, firstly, of availability of data, which are not always ready to be used or available on the web or in the public organization like a Tuscan region. This is first thing that I want to say. That what is important is to proceed in that direction, and as I mentioned in the end of my presentation, a dedicated project to a specific site would help surely, because in that case we can work at the site level. It means we can perform a geological model to untapped is not correct, but to clarify what are the structure in place, and the geological structure that can play an important role in this process. After that, surely numerical simulation are important to characterize all the parameters in the underground, beside, of course, the laboratory analysis. But at this point, I leave the floor to Chiara or Andrea. So a project is
I'm more practical. More practical, and I think we have to try. So we are at the time that we have to try with pilot plant. The only things that we don't know, and it's the public acceptance. This is something that we suffer during GECO project, as Amel know very well, and as all of us know very well, because we have to do a small pilot plant and to see the fracturation and porosity and the evolution of porosity. As we see during the project, is this kind of process, it happens in nature. What happened For the increased fracturation or induced fracturation, we don't know. But we have decades of experience in other fields that the fracturation is induced. So why we have to be worried about that? So we have to try in safe and good place, away from protection zone, away from seismic zone, and try. Also because we want to solve this problem or not. So this is a main question. Do we want or not? Because in Tuscany we have not gigaton of CO2 emission, but million tons of CO2 emission. And up to now, there is no decrease of CO2 emission in Tuscany. So what we want to say from the political point of view or from social point of view, if we want to solve the situation, we need to test also this kind of technology. This is the only reason. We saw this, and we saw the evolution of CO2 emission doesn't change since 100 years. I don't know.
Yeah, this is definitely a pertinent point. I mean, social acceptance has been hindering parts of the project efforts in Italy, and this is definitely a conversation to have. Like, what do we want, and how do we want to do it? And because this topic touches upon the geothermal production, but also the other heavy industries, and at the same time we want to do things right. So you want to understand what would be the implications of such practice. This is also touching upon the raw material aspect, if you want to do the ex situ mineral carbonation, and a lot of actors should be present at the table to discuss such things and then get to a consensus. But this is definitely an opportunity. I mean, it's working. There is a high potential for it, at least now that we see in Tuscany, and so that's an invitation for discussion in the future, for sure, with the officials. Andrea, any other words from your side?
Yeah, I completely agree with Chiara and Eugenio, and you as well, because yeah, from my side, I think we have all the basic scientific knowledge. I mean, like to know what we are doing, but there is the strong necessity of a concrete application, something that we can test with a pilot plant, like Chiara said. And I think also Southern Tuscany in particular, how Eugenio, basically what he showed us, it is possibly the perfect place for a case study in ultramafic rocks. We have all the knowledge, local geology, and also geochemical geology, and also with what Eugenio did, also we know pretty much exactly where are the most favorable sites. So I think we have a great spectrum of knowing and understanding the basic science. And now, if we believe in this opportunity, we need to take action. Yeah, completely agree.
Yeah, so I am not seeing any questions in this at this stage of the webinar, but I think the concluding remarks are quite clear, and there is a promising future for this. So yeah, thank you all for your talks today. But before we leave, I want to give some perspective regarding what's happening in GECO in the very near future, and still in Italy. So we have the summer school, the GECO summer school that is coming up. It's going to be in Volterra in Tuscany between the 17th and 21st of May. So registrations are open for those who are interested. This is a summer school that is open to early careers and any professionals interested in the CCS in geothermal and its application, and what we're doing basically in GECO. So through these webinars, first we want to transfer the knowledge that we are acquiring in the project, and through the summer school we want to also give a very in-depth perspective of the mineral storage and also the engineering parts to interested parties and build the next generation of people who will take this forward. So yes, please go to the GECO website and check the registration and submit your applications. Yeah, and thank you very much to all the attendees and our speakers today, and looking forward to the next webinar with you.
Eugenio, want to say something? Eugenio?
No, well,
okay. No, I just want
sorry.
to add, if someone of the participants want to have a certification as a PhD student, please contact me or Amel, and we will send to you the certification.
Yes, definitely. And the webinar is recorded, so for the ones who couldn't join or continue, you will find it on the GECO YouTube channel. So yeah, so thank you very much. And
Thank
see you
you.
soon.
Thank you.
Thank you.
Bye.
Bye.
Have a good
Bye.
night.
Bye-bye.